Good evening, everyone. In a wastewater treatment plant, energy costs are no longer a secondary concern. They are a defining operational challenge. And at the heart of this challenge lies one critical process aeration. When oxygen transfer efficiency improves, everything changes. Energy demand drops, process stability increases, and plant capacity expands without civil upgrades. Today's session is not just a technical presentation, it's a focused discussion on how modern diffuser design and advanced Ifas biofilm technology can fundamentally improve biological performance while reducing operational costs. Welcome to our webinar, Optimizing Biological Treatment Efficiency Using High Efficiency Air Diffusers and Ifas Technology. During the session, we will examine why diffuser efficiency is the true driver behind energy savings in a wastewater treatment plant, how Ifas technology, particularly Shearcon, enhances nitrification capacity and sludge settleability, and real case studies demonstrating measurable energy reduction. We are honored to host experts from Jager Envirotech, Germany, a leading company in high-performance aeration diffusers and biofilm systems. It's truly my honor to introduce our distinguished speakers today, Mr. Hans Christian, Managing Director of Jager Envirotech, Germany, and Dr. Engineer Ihsan Mohammed Bajo, Product Developer and Sales Manager at Jager Envirotech. We are truly honored to have you both with us today. Dear attendees, just a quick note, to get your attendance certificate, please fill out the registration form that will appear in the meeting chat. We will begin the first part of the session with Mr. Hans Christian, who will present Jager Envirotech and set the technical framework for today's session. مساء الخير على حضراتكم جميعا. في أي محطة معالجة صرف صحي بقى موضوع الطاقة مش حاجة جانبية، ولكن تحدي تشغيل أساسي، وفي قلب التحدي ده عملية واحدة تأثيرها كبير جدا، التهوية. لما كفاءة نقل الأكسجين تتحسن المعادلة كلها بتتغير، استهلاك الطاقة يقل، العملية البيولوجية تبقى أكثر استقرارا، وكمان نقدر نرفع الطاقة الاستيعابية من غير توسعات مكلفة. جلسة النهاردة مش مجرد عرض تقني، لكن نقاش عملي عن إزاي تصميم الديفيوزرز الحديثة مع تقنيات الآيفاس يقدر يحسن الأداء البيولوجي بشكل كبير ويقلل تكاليف التشغيل. أهلا بيكم في ويبنار تحسين كفاءة المعالجة باستخدام ناشرات الهواء عالية الكفاءة وتقنية Ifas. النهارده هنتكلم عن ليه كفاءة الديفيوزر أحد أهم عوامل الاستهلاك ازاي الطاقة. وشرفنا إن معانا النهارده خبراء من شركة ياجر انفايروتك الرائدة في أنظمة الديفيوزرز وحلول البايوفيلم عالية الأداء. ويشرفني أقدم المتحدثين معانا النهارده مستر هانس كريستيان المدير العام لشركة ياجر انفايروتك ألمانيا، والدكتور المهندس إحسان محمد بجوح مطور المنتجات ومدير المبيعات في نفس الشركة. تنويه: للحصول على شهادة الحضور من فضلكم لازم نملى فورم التسجيل اللي هيتبعت في الشات خلال الويبينار. كمان لو محتاجين ترجمة للغة العربية ممكن نختار ده من اوبشن سي. هنبدأ الجزء الأول من الجلسة مع مستر هانز كريستيان اللي هيدينا نبذة عن ياجر انفايروتك ويضع الإطار الفني لموضوع النهاردة. Dear Mr. Hans, you can start your presentation now. The floor is yours.
Thank you very much for the kind introduction. You mentioned our names already. Nevertheless, I would like to repeat. My name is Hans Christian von Konsbruch, and together with my colleague, Dr. Ehsan Pajou, we will be the presenters of today's webinar with the topic Optimizing Biological Treatment Performance in Wastewater Treatment Plants with High Efficiency Diffusers and Shearcon Ifas Technologies. I would like to start with a short introduction into the Jaeger company. Maybe start with saying a few words about myself. After the introduction of the company, we will modify the agenda a little. We will switch directly into the topic of Ifas technology, and after this topic, we will continue with the topic of aeration. Ifas technology is a little more sophisticated. I hope you all will have the energy and time also to follow the second part about the aeration technology. Let me give you a few brief information about the Jaeger Group. The Jaeger Group has its headquarters in Germany, Hanover, Germany. Consists of 16 entities, all located in the Northern Hemisphere. 3 of those in the United States, several in Europe, and 1 in India and 1 in China. Currently, we have 1,300 employees, and the revenue of 2025 is at about 215 million euro. The group is active in various fields. The biggest field is agricultural machinery, but we are also active in energy technology and industrial machinery, all based, the entire business based on rubber and plastic parts. And rubber and plastic parts is something that you also find quite often in the environmental technology, especially when it comes to aeration technology. And that is how Jaeger Envirotech came to life, so to speak. Jaeger is active in the field of aeration since 1975. This should mean started. There's a T missing. We have currently 40 employees. We are also located here in Hanover, Germany, where the headquarters is, and we're working out of Germany. Where do we stand out compared to other aeration companies? We are indeed producing diffusers from the scrap, which basically means from the raw material, all here in Germany. We are compounding our membrane materials ourselves. We are producing the membranes, we are producing the plastic parts, doing the entire diffuser assembly, and everything which belongs to producing a high-quality diffuser. Of course, last but not least, the entire quality control and quality insurance that we are conducting here in Hanover, Germany. The membranes, which are the most important part of the diffuser, are all or have always been developed here and continuously improved in its performance in the used materials. And all we are doing today is based on a 50-year-long experience. What makes it so special that we are doing all ourselves basically means we have the full control over every production step of each and every diffuser, and that is of course the basis for a top quality, and that is what differentiates us to a certain extent from basically all other diffuser companies in the world. Now, before going now into the aeration topic, I would continue, as I mentioned in the beginning, I would like to continue with the Shirkon topic, and this is presented by my colleague, Dr. Ehsan Pazou. So, Ehsan, now I hand it over to you.
Thank you very much. So I'll try to share my screen. Just 1 second, window, share. Could you please let me know if you see the presentation in a full screen mode?
At the moment, I don't see no presentation yet.
Okay.
Have you shared your screen already?
Yeah, I'll do it again. Because, so you mean you see my screen as a
but you didn't share as a window. You shared as entire screen.
Okay, just 1 second. I'll try to do it again. I apologize. We changed the room. That's why I had to come to the meeting room. So show my screen. Stop presenting. 1 second. Sorry. Present now. So I'll try to share the entire screen. So maybe.
Yeah, please share the entire screen.
Window share. So that's probably.
Share window.
Do you see it as a presentation?
Now we see it. Yeah, perfectly.
Okay, that's good. Yeah, I apologize. As I said, the office was crowded, so I had to come to meeting room. That's why. So I think I'm gonna skip the introduction, as we already discussed that. But in this, what do you call it, session, I would like to share with you, what do you call it, background and limitations to conventional activated sludge system. And then the technologies that actually exist when you want to increase the treatment capacity of your wastewater treatment plants, and also technologies that allows you to upgrade your existing wastewater treatment plant to achieve nitrification. Afterward, I'll show the shear comp process, how it works, and how you can basically achieve much higher nitrification rates, and also improve the sludge settling velocity. And then we can basically discuss that if there are multiple technologies in the market, how you can select the technology that suits you, and then we can get into discussion and exchange. So basically, a very short introduction about the mixed liquor suspended solids and biology. So this is something that we learned from the nature, and then we brought it to the wastewater treatment plants. So if you go to the river, there are always bacteria and suspended solids. Some river have much higher quality, some not. So depending on the water quality, you can sometimes see that it's a little bit turbid. And that's the main reason that you don't actually drink the water from the river, because it contains bacteria, solids, and so on. And some of these bacteria are actually good for biological wastewater treatment. So what we do in nature is that we try to concentrate these bacteria, which you can see here. So if you go to any wastewater treatment plants, the heart of the wastewater treatment plant is basically the biology. These are the main workers who do the biological wastewater purification. And if you take a sample, it always looks like this brownish biomass. So they call it mixed liquor suspended solids because it's a combination of suspended solids, active bacteria, dead bacteria, and sometimes they call it activated sludge because it's active under different conditions, and sometimes they call it biomass, and this is how they look like under microscope. So to have a look at the typical wastewater treatment plants as an introduction. So if you go to wastewater treatment plants, typically the wastewater has lower elevation compared to the steps that you need to purify that wastewater. So at the first step, you use this Archimedean pump to bring the wastewater to the right elevation. And then in the next step, you try to get rid of all these things which are either not supposed to be thrown to the toilet and end up at the wastewater treatment plants, or basically protect your next treatment steps, which are aeration or biofilm technology. And then in the next step, the pre-screened wastewaters goes to the grid chambers. Here you create a spiral flow so that the sand and organic matters are separated. And then in the next step is the primary treatment tank. So this is an important steps in many wastewater treatment plants, or in some of wastewater treatment plants in Middle East, still this step doesn't exist. Some wastewater treatment plants have this step, and this is essential because using the gravity and almost no energy, you reduce concentration of suspended solids and part of organic matter. So depending on retention time, you can reduce concentration of suspended solids by about 50%. The COD, you can reduce it up to sometimes 25 to 30%. But whatever is dissolved, like for example, ammonium phosphate, it goes to the next step. And this is basically the heart of wastewater treatment plants. Here, it's called biological purification. And then you can see that there are different colors here. These represent different type of biomass in your system. As mentioned earlier, this brownish biomass is called mixed liquor suspended solids. There are different type of microorganisms there, which if you create different environment, different purification takes place. So if you take a look at here, the first step is anaerobic. The second is basically the anoxic zone, and then there are aerobic zone. And this aerobic zone is very important because there are a specific type of microorganism living here called ammonium oxidizing bacteria and nitrate oxidizing bacteria. And these are essential to perform nitrification. The reason I put Hans in the next session, he will then focus on aeration technology. As you know that there are the major costs in wastewater purification is mainly related to the aeration tank, and there you will basically get to know how efficient aeration system can reduce the operational costs significantly. So in biology, when the wastewater is biologically treated, then the wastewater goes to the huge tanks. These are called clarifiers. So here you allow the biomass who did biologically purify the wastewater to settle, and then basically concentration of total suspended solids, ammonium, COD is reduced significantly, and then you can basically discharge this treated water to the receiving water bodies. One of the challenges or limitation is that when there is a high population growth, there is more wastewater coming to your wastewater treatment plants. And when, for example, there are higher percentage of urbanization, people are basically coming to the cities for better life. They consume water, they also produce wastewater. And sometimes when you design a wastewater treatment plants and you did not consider, for example, emerging or upcoming industry, then you might also face problem because there might be new incoming load to the wastewater treatment plants. And here the problem is that, as mentioned earlier, the heart of the whole system is biology, but you can have a specific concentration of biomass in your system. So a typical concentration is about 2 to 4 kilograms per meter cube. If you have more wastewater and then if you need more biomass, then it is not possible to simply just increase the concentration. So you need to then think if the land is available or not. So here in this wastewater treatment plant, you can see that there are enough space for future, for example, construction. But at the same time, sometimes the construction cost is so high that it just doesn't make sense to construct. And rather, you can look for another technology, which is basically the biofilm solution. The other limitations of many conventional activated sludge plants is that in the past, they were mainly designed for carbon removal. So there are many inquiries that, for example, we still receive from Middle East, and some of those plants are basically designed only for BOD elimination. And this was historically done because if you don't eliminate it, then this is going to reduce the oxygen concentration in the river. So the initial stage historically was to remove BOD, but then over time, it was realized that it is also important to have nitrification, denitrification, because ammonium, if, for example, is discharged, could also reduce oxygen concentration in receiving water bodies, but it's also toxic. And also if converted to nitrate, then it could result together with phosphate eutrophication and algae bloom. That's why the next step was nitrification, denitrification. And then many wastewater treatment plants, for example, in Europe, they also have biological nutrient removal, means that they have nitrification, denitrification, but also biological phosphate elimination. And the current approach is also trying to reduce emission from many wastewater treatment plants and reduce the nitrous oxide emission and also emerging micropollutant. But one of the main challenges is that if the wastewater treatment plant is designed for carbon removal and now needs to be upgraded to nitrification, denitrification, then this means that you need higher concentration of two types of microorganisms. These are known as ammonium oxidizing bacteria and nitrate oxidizing bacteria. And in a conventional wastewater treatment plants, they are minority. So to be able to have them in your system, you typically need higher sludge retention time. So to give you a better understanding about their growth rate and why we need, for example, biofilm technology, is that if you take a look at, for example, ammonium removal from wastewater treatment plants, when we talk about conventional systems, so there are 3 ways to remove ammonium from wastewater. One is conventional 2-step nitrification, the other one is anomox, and the other one is comomox. These 2 steps are type of ammonium removal is different. We don't get into detail, but when we talk about the conventional 2-step nitrification, is that you would like to have 2 groups of microorganisms in your system. So the first one is called ammonium oxidizing bacteria. They are in charge for conversion of ammonium to nitrate. And then the second type of microorganism which you are looking for is nitrate oxidizing bacteria, which then they take this nitrate and then convert it to the nitrate. And if you take a look at their net growth rate, you can see that it's about 0.5. This means that theoretically it takes about 2 days under optimal condition to have these bacteria in your system. And they are really sensitive. So you can see that if there is a changes in the pH in the plant, their activity totally reduces. And even nitrate oxidizing bacteria are more sensitive. So sometimes, for example, if something goes wrong at the plant, you can immediately see that there is a spike in ammonium concentration and also nitrate concentration. And this is due to the fact that they are minority and they are really highly affected by operational condition. So one of the main points that we discuss is that now that you want to have this sensitive biomass in your system and upgrade the system for achieving nitrification, one of the main factor is sludge retention time. You have to give enough time to these bacteria to basically grow and remain in your system. And one of the main influencing factor is the wastewater temperature. So I can show you in the next slides that what should be the ideal, for example, a sludge retention time based on German standard to achieve nitrification. But the general rule is that the sludge age must be larger than 1 divided by mu, or growth rate. So here, for example, the specific growth rate of the ammonium oxidizing bacteria and nitric oxidizing bacteria is about 0.5. This means that theoretically you have to have about 2 days or 2.13 days. This is more better theoretical calculation. But the problem is that in your wastewater, there are different kind of, for example, contaminants. So when people, for example, send the wastewater to the wastewater treatment plants, there are shampoos. When there are industry, for example, they also discharge some heavy metals, although it is diluted, but this is not basically then ideal condition. That's why based on German standard, you have to add another biological safety factor, which is about 1.6. And that's why in the sludge age calculation, you end up requiring minimum realistic of about 3.4 days for the sludge age in your system. And then there is another thing that you have to consider, and depending on the size of wastewater treatment plants, because when you have, for example, a small wastewater treatment plant, this is called 2000 population equivalent, then you have to consider additional safety factor for your sludge age for nitrification. So if you recall, 3.4 is the minimum practical or realistic sludge age that you need for nitrification. And then if, for example, you're talking about the small scale wastewater treatment plants, which you have a lot of load fluctuation, you have to add 1.8 here. And then if, for example, it is larger wastewater treatment plants, or if you have some buffer tech that you are able to cope with those fluctuations, then you can consider 1.45. And this is important because this shows how you can calculate the sludge age that you require to upgrade your plant to achieve nitrification. And then the next step is basically the wastewater temperature. So if you live, for example, in the cold climate, the bacteria are less active than if you live in the warm climatic condition. And the best way to have a better understanding is when you consider that these are basically living microorganisms, and then you compare them with yourself. So if you basically stay in the cold water, you basically don't move much. But if you are in a warm water, you tend to move more, and then you are more active. The same is true with the bacteria. So for example, if you consider the two different wastewater temperature, or case of, for example, Saudi Arabia, or most likely, for example, Egypt, then you can end up having different correction factor for a sludge age calculation. So here is basically the correction factor. So you can see that 15 degrees Celsius, you have no correction factor. But if, for example, your wastewater temperature is having a higher temperature, then you need a slightly less sludge age. If, for example, it is colder, then you need more sludge age. So typically, for example, in the warm climatic country, let's say, for example, Saudi Arabia or Egypt, to be on a safe side, you need a sludge age of about 4 to 5 days to achieve nitrification. And when we talk about the Germany, you typically require higher sludge age of about 7 days. But the problem is now that, for example, you need higher sludge age and you need more volume, will you be able to cope with this condition to upgrade your wastewater treatment plants? Then one possible solution is to copy the other things that happens from nature to be able to bring more biomass in your system, and old biomass to be able to do nitrification. So again, this is something that you can learn from nature. If you go to the river and then you go with the barefoot and then you touch a stone surface, you can see that it is slippery. And this is basically biofilm formation. And this is basically how concept of trickling filter was developed over time. But the problem is that the surface of the stone is very limited. This means that if you use such, for example, stone as a biocarrier to allow biomass to attach and grow, then you will be having a limited surface area for your biofilm system. That's why over time, people found out a more or a smarter solution, and then they engineered some sort of biocarrier which has a lot of surface area so that the biomass could attach and then biofilm could be formed. So here, for example, you could have more biomass in form of biofilm or sessile biomass in your system. Then afterward, there was introduction of, for example, other solution like rotary biological reactor, RBC. Then there was, for example, another solution called MBR, which allowed you to keep higher concentration of biomass in your system. And then another solution which was discovered was MBBR. So they said that, okay, if, for example, you put this biocarrier into the basin to allow biofilm formation, then maybe it would be better to put these moving bed biocarriers so that the biomass can attach. So it results in a good nitrification rate, but there are some drawbacks to this technology, which I can explain later. But one of the most recent development was another technology, which is called aerobic granular system. And the advantage of this technology compared, for example, to MBBR is that they don't use the plastic media. They say that, okay, we create a specific condition for bacteria. We put them under stress that they form a nucleus. And then around the nucleus, we have, for example, an aerobic, anoxic, and oxic zone or aerobic zone, where, for example, simultaneous nitrification, denitrification, and phosphate removal can take place. And then there was another emerging technology called MABR, which, for example, is relatively expensive. I think there are not so many references, but this is also a good energy efficient technology where, for example, you bring oxygen to the bulk solution using the gas permeable membrane. And then one of the last development was hydrocyclone. The advantage of this technology is that it separates light fraction from the heavy fraction, and then it allows you to increase concentration of the MLSS in your system. Problem is that it is only about the separation of the light and heavy fraction and no improvement in the biological activity. And then the latest development was basically the ShearCom process. ShearCom process is an advanced integrated fixed bed activated sludge system. So this means that it has all those benefits of the old technology. But the advantage is that here we have biofilm, but we also have granular-like biomass that settles really fast, over 5 minutes. But it's still fairly simple, and it can be also operated at much lower dissolved oxygen concentration compared to the MBBR. And I can basically show maybe a short video so that you get a better feeling about the performance of the plant. So this is, for example, a wastewater treatment plant of the Geisebulach. It is located near to the Munich. And here in their aerobic chamber, they use Cleartech media. And then because of choosing the right operational condition and having the right design, they are able to have right sloughing effect, and they are able to achieve MLSS concentrations which varies between 4.5 to 6 kilogram per meter cube. And despite that, you can see that our colleague took a sample, and this sludge settles relatively fast. So over 5 minutes, major part of the sludge settles. And this is really a great advantage because it allows you to basically run the plant at higher MLSS concentration, but at the same time, it reduces the SVI value. It implies that it is less likely that you lose sludge at your clarifier. But then the reason that basically we, or the way that we discovered this advantage of the system was that, as I explained before, when we talk about the conventional system, this was something that we copied from nature. It was basically the suspended solid that we tried to concentrate. And then the biofilm, if you recall, we talked that there was stone, and then there was, over time, improvement in design of the biocarrier, and people came with different solution. But one thing which was actually ignored and we found out and we patented was that the biomass which is detached from the biocarrier has different kind of specific behavior. And if you have a right design, and if you harvest that detached biomass at the right time, you will be able to increase concentration of ammonium oxidizing bacteria and nitrate oxidizing bacteria in your reactor. So you will achieve higher nitrification rate. And at the same time, these detached biomass is much more dense. So over time, you can improve the sludge settleability, and therefore you can run the plant at much higher MLSS concentrations. Here I have two case studies that you can see that, for example, here in this plant, the ammonium concentration in the inlet is about 40 milligram per liter. And then depending on the season, they are achieving 1.2 to about 0.3 milligram per liter at the outlet. This is normal because in the summertime, biomass is more active. In the winter, they are less active, but still it's a good effluent quality. There is another wastewater treatment plant called Weissenborn, and then they are also having about ammonium concentration of about 1.3 milligram per liter. And SPI improvements in these plants were by almost more than 50%. So you can see that here, for example, from 126, they were able to reach about 70 milliliter per gram. And then in Geisebulach, they were able to reduce it from 200 to almost 80 milliliter per gram. So again, the advantage of these advanced Ifas system is that you will have a combination of biofilm as well as conventional MLSS plus the heavy fraction of the sludge, which we call it third fraction, which improves the settling velocity of the sludge, but at the same time improves nitrification rate. And also apart from that, allows you to run the plant at much higher MLSS concentration. And also it's still relatively simple and energy efficient. So energy efficiency is key in many wastewater treatment plants. I think Hans Christian can provide more explanation about the aeration part, but at the same time, the biology is also important. So there are multiple different technologies which can be utilized to increase the treatment capacities, but it's always important to understand at what dissolved oxygen concentration those technologies operate well. And by, for example, shear com process, you only need to operate it at about 1.8 to 2 milligram per liter. I can show you in the next slides that how this affects the operating costs. I would basically, to save the time and stick to the plan, I would skip going through all these technologies which are, for example, available in the market, but we can discuss in detail if you have a specific question. That's the main reason I put this slide here. But I think one of the main important topic to discuss is that customers or clients are not only limited to one technology. So there are multiple different kind of technologies, like, for example, various type of MBBR biocarrier on the market, or aerobic granular sludge, or shear com process. But the question is that how they have to select the right technology. I think there is 3 steps that that defines how you should screen anything, whether it's, for example, product or whether it's a solution at the wastewater treatment plants. The first step is basically customer needs, and the second is the common shared features, and last one is differentiation. To translate this better is basically, if you consider, for example, the restaurant. So when you want to eat something, you basically go out and look for example, a restaurant, because your needs is to find a food or restaurant. And then, for example, if there are multiple restaurants there, then you compare and then you see which one fulfills your wishes. So for me, it's always like this, that when, for example, I would like to eat something, I go out with my son, and then in the nearby, there are always, for example, KFC and McDonald's. And then at the end, although they are located at the same place, then KFC doesn't have Happy Meals, but for example, McDonald's has Happy Meals, and that's why my child always decide for example, McDonald's. The same is true, for example, for the wastewater treatment technologies. So you have to see what is your customer needs. So when we talk, for example, about the Middle East, the need is basically to fulfill effluent quality. When we talk, for example, about EU, the need is not only to fulfill effluent quality, but for example, emission control is also important. Elimination of emerging micropollutants is also important. So if we focus, for example, the effluent quality as the main criteria, for example, for customer needs in the Middle East, for example, then you have to make sure that you have the healthy biomass. Problem is that there are many technologies which are based on biofilm solution, but if your biomass is not healthy, at the end, you will not be able to meet the effluent quality, because as I discussed in the first slide, the heart of any biology or any wastewater treatment plant is its biology. So you have to make sure that the main workers or the main biomass which are there are healthy. And to give you a better example, you can basically, as I said earlier, you should compare the microorganism as the living microorganism, and you can compare it as a human. So if you consider, for example, human, if you got many humans in one room, then those which are basically near to the door receive the oxygen and then receive the food. Then at the same time, it is also important to notice which kind of food you're basically giving to these population. And if, for example, you take a look at the people back there, they don't get the oxygen, they don't get the food, so they are not in a healthy condition. So it is always important to keep the right population of the people in that room. The same is true basically for the biomass. So there are multiple, for example, companies who are providing solutions. I put it as an anonym to mainly show it as an example. So if somebody basically try to copy what we are doing, at the first glance, it looks like a biocarrier, but when you basically know the system, then you can immediately say that this is a dead biomass, this is the active, healthy biomass. And the main reason behind is that if you put anything in the biology, the biofilm will form. So as I said earlier, for example, if there's a stone in the river, the biomass see the stone, they want to survive, they attach, and then they stay there, they grow. So here, for example, you can see that we take lots of sample from our pilot plant, and here you can see these metal, for example, cages that we take out, and then you can see that the biofilm is formed. Question is this biofilm, for example, active or not? So what is really important is that if you are producing something as a product, you have to make sure that the biomass which is attached remains healthy, because at the end, you have to understand that there is always diffusion limitation to the biofilm. And what you measure at, for example, bulk solution does not represent what actually goes to the biofilm. And that's why above there, you can see the example of the human to get a better understanding. The same is true basically for the biomass. So if, for example, you have ammonium, if you have oxygen, typically the upper layer of the biofilm get most of the substrate, but there is a diffusion limitation. And then if the oxygen does not reach, then you end up having, for example, a dead biomass, and therefore you will not be able to fulfill your effluent quality. So your need is basically to fulfill your effluent quality, and for that you need a healthy biomass in your system. The other factors which are basically important is the capacity of the system. If, for example, multiple different technologies which are proposed for capacity increase, they also are able to fulfill the same capacity. The other aspect is basically the plant modifications. There are many good technologies also at the market, but problem is that sometimes they're also requiring plant modification. If you, for example, take a look at the MBBR, you typically need to have these sieve on your aeration tank to make sure that you don't lose those biocarrier. And whether this is possible or not, that's something that you have to consider. Aerobic granular, as I mentioned earlier, is also one of the emerging technology. But one of the main challenges is that you have to make a lot of modification to the plant, because the waste bottom must be fed to the biomass from the floor of the basin to make sure that it reaches to those biomass. Because if it does not reach, at the end, the inner part will become inert, and then it's going to be disintegrated. And then the problem is that it's going to take for you months to establish the same system. So if there is no nearby plant to seed your wastewater treatment plant, you might need, for example, 3 months or more to be able to generate again the granular slide. So that's basically another factors that you have to consider, that if, for example, different technologies fulfill your treatment target and you're able to achieve effluent quality, basically they fulfill similar capacity, then do they require plant modification or not? How's the startup? How's the risk with this system? And then the other factor, which, for example, is important, is that you have to compare the shared features between the technologies. So here I will not get into detail, but I just want to give you an example for Ifas system and also MBBR, because both of these technologies are relatively popular. So when you, for example, compare the common shared feature, one of the main factors you have to consider is equivalent annual cost and also a specific treatment cost. What does that mean is that when, for example, you put the Ifas in your system, the fixed bed biofilm system. Based on our knowledge, for example, because we have, for example, some investigation, we know that at least after 17 years, there is no change to the material characteristics. This means that you don't need to do any reinvestment when you purchase this technology. And this is something that's important because, for example, by some biocarriers, like I don't want to name the manufacturer, but here you can see that basically there is an abrasion. They constantly move to the concrete tank or against each other. So over time, you might lose some of those surface area. One of, for example, the biocarrier, which I think has a good design, is, for example, Mutag biocarrier. So because it is protected from the edges, and then it could have maybe a bit better lifespan compared to those cheap biocarrier. But again, one of the other factors you have to consider is that, okay, if, for example, even both technologies have the same lifespan, which is actually not the case, because I think when your biocarrier is fixed into the place and it doesn't move, it has higher lifespan. So by ClearTech, I think you can consider simply above 20 years and you don't need any reinvestment. But even though, for example, if the reinvestment situation is the same, you have to consider the specific treatment cost. And a specific treatment cost basically relates mainly to the aeration part as well. And if I take, for example, some real value from publicly available information, you can see here that for MBBR, for COD and BOD removal, you need dissolved oxygen concentration of 2 to 4 milligram per liter. And for nitrification, about 5 milligram per liter. And the reason is that basically you have to first make sure that these biocarrier, you have enough air in your reactor so that they constantly move and come to the substrate. But if I take, for example, these values and then I translate it to the operational cost, then here you can see that if we consider a 250,000 PE wastewater treatment plants, for example, Geyser Bulach, which we know the design, if, for example, you are using the fixed bed system, like Ifas system that we are offering, you need, for example, a specific air of about 5.5 norm meter cube per hour per meter square. By, for example, MBBR, if you name it anonym, then if you have a very efficient system, you need at least about 7 norm meter cube per hour per meter square. If you consider the average or typical situation is 11, extreme case, which I showed you before, could be 15. But even if, for example, you consider a fairly good, for example, design, which requires 11, and for example, the Ifas system, which is fixed, you can see that the air demand is twice as much. And this, for example, requires a larger blower, larger investment. But at the same time, if, for example, you translate this to the electricity cost, then you can see that the operational cost for the fixed bed biofilm system will be about 270,000 euro per year. And for example, the case where MBBR requires about 11 norm meter cube per hour per meter square, then this could be about 500,000. So I think roughly about 3.5 years, it's going to be, the differences will be about 1 million euro, which is a lot. So this is something that you have to always consider when you decide for a technology. And the last point is actually the product differentiation. So as mentioned earlier, it is important to compare, for example, if the product fulfills your needs. If, for example, there are common shared features, you have to, for example, consider the equivalent annual cost and also the specific treatment cost. And lastly, when, for example, similar technologies are having similar, for example, performance, then you have to look for product differentiation. And one of, for example, things that we do is that we try to have a better process design. So at the end, you would like to have a very efficient system, but efficient systems sometimes work best when you have combination of efficient products. So here, I think I will skip the first part, which is basically about the energy efficient, long-lasting diffuser. This is something that Hans Christian will explain in detail, that how, for example, different SOTE value will allow you to further reduce your operational costs. But in our system, when we, for example, offer shear con, we try to couple energy efficient diffuser plus the biofilm, which requires, for example, less DO concentration. But at the same time, for cases that, for example, relate to the Middle East, we sometimes try to work together with the solid blower manufacturer, like, for example, Next Turbo Blower, and also, for example, with Binde Group, to make sure that we also reduce the emission from the wastewater treatment plant and also have a healthy biofilm in the system, because sometimes you need a good automation to have a sloughing effect. But at the same time, for example, the blower must also work well. So if, for example, the blower does not have a good air filtration, for example, and all those sands come into the aeration system and then the diffuser fails, then the next step, for example, biofilm gonna fail. So sometimes it makes sense that even look for combination of good and energy efficient system to have a very robust solution in your project. I think this part I'll basically show a very short introduction about how we proceed with the design. So maybe just like 5 minutes. So if you are interested to, for example, implement the energy efficient shear con process together, for example, with our energy efficient aeration system, then at the first step, we typically need a checklist from you. So some of the customers are basically able to fulfill all those required parameters. But sometimes if, for example, some informations are missing, we can follow, for example, German standard. Here you can see that there are some tables. Here it says, for example, if you don't have the quality, effluent quality from your primary clarifier, then we can take the assumption and use, for example, German standard, and then fill some of those parameters which are missing. So at the first step, after receiving the checklist, depending on if you would like to have shear con process or, for example, energy efficient system, we follow our own design, which at the heart of our design is basically the DWA or German standard, which has been used. So for the shear con, it's a combination of product specific parameters that we use, but at the same time, we use DWA 131. This is the standard German standard for biology. And for the aeration design, we follow the other standard, which is DWA M229-1. And then once we design, for example, these two parts, then depending on the size of the project, we might be able to also do some pilot tests and also simulations so that we can analyze various scenarios. And then at the end, we can provide extensive report where you can basically have a detailed understanding about the sludge age, amount of biomass, substrate removal rate, and all those parameters. But as mentioned earlier, two parts of design are very product specific. So when we talk, for example, about the shear con process and biology, we have two different kind of biocarrier that you can place into this system. And we have done multiple tests. So we know, for example, how much biofilm is grown on different media that we have, and what is, for example, the substrate removal rate. Similarly, when we talk about the diffuser system, we have a lot of different diffuser in our product portfolio, and we have done a lot of tests with different universities, and we know, for example, how's the efficiency of different products that we have. So at the first step, we try to take a look at the checklist and see what kind of load you have in your system, because as mentioned earlier, when you take a look at the biology, you have combination of different kind of bacteria, and each of these bacteria require different amount of oxygen to do the job. So for example, when you require ammonium removal, you have to consider about 4.3 kilogram of oxygen per kilogram of ammonium. Then depending, for example, your organic load, you have to sometimes consider about 0.5 to 1 kilogram oxygen per kilogram BOD. And therefore, we have to see what is the existing load in your wastewater treatment plants. And then based on our product specifics data, we can basically calculate the amount of air that you need. And this is basically the part that Hans Christian will get into detail, because as mentioned earlier, major part of the major operational cost of any wastewater treatment plants comes from aeration technology. This could be hundreds of thousands of euros per year. And there he will basically show you that how efficiency of different kind of products that we have varies. So here you can see, for example, in the first tank, we have done some tests with University of Darmstadt. When you can see, we tested different diffuser density, tube diffuser. Here, for example, you can see different diffuser density of the disc diffuser, and they do have different efficiency. So after the coffee break, I think Hans Christian can provide a detailed explanation about the aeration technology, and then you can see how much you can basically also save based on having the energy efficient aeration system. So from my side, thank you very much. And if you have any question, please write down. We'll respond to all the questions at the end of the webinar.
Thank you, Dr. Ihsan, for the insightful technical presentation. At
Thank
this
you.
point, we'll take a short 10-minute break. Please stay with us. We'll resume shortly to continue with the aeration and diffuser performance section. See you again in 10 minutes. دلوقتي هناخد استراحة لمدة 10 دقايق وهنرجع نكمل الجزء الخاص بالتهوية وكفاءة الديفيوزرز بعد الاستراحة مباشرة.
I can't mute my, I don't know why I can mute it, but stop present.
Yeah, it's okay with you?
Yes, I can't mute actually. I don't know why it's not. If you can mute my,
Yeah, okay.
I would appreciate.
Welcome back, everyone, and thank you for staying with us. We will now continue with the other technical part of today's session. I'd like to invite again Mr. Hans Christian to present the role of diffuser efficiency in reducing energy consumption, performance comparisons between different diffuser types, and real case studies demonstrating measurable energy savings. Mr. Hans, please continue.
Thank you very much. Yeah, thank you for staying with us. I hope you learned a little from the very detailed presentation of my colleague, Dr. Ehsan Paju. If you had no idea about how wastewater treatment plants work, now you should have it. I'm focusing now on one part of each biological wastewater treatment plant, which is the aeration. And the reason why we are focusing now on this part is basically in the header of the entire presentation today. It's all about energy consumption. When you take a look at the literature about wastewater treatment plants, you find percentages about the energy consumption of the aeration of the entire wastewater treatment plant. And these figures are usually around 45 to 75%. Other areas, other technological devices take up significantly less energy. On the left-hand side, you see a graph which shows basically what it is, but it varies from wastewater treatment plant to wastewater treatment plant. But you can see the aeration takes up the major part of the energy. And because of that, of course, you have with the aeration the largest leverage for energy savings in your facility. Why is the diffuser indeed the key to energy efficiency? It all basically starts with the design of the aeration system. It was in the past, years ago, quite common to start, when you design an aeration system, when you design a biology, to start with the blower, basically assuming a certain efficiency, calculating the airflow rate. And based on the calculated airflow rate, you basically picked the blower, and then you said, okay, I pick an efficient blower, and you saved a few percentage of energy. This is not the right approach. Certainly, the right approach comes from the wastewater characteristics, from the flow rate of the wastewater, and from the inflow concentration, CO2, BOD, TKN, and total phosphorus, and of course the effluent concentrations you would like to achieve. From these information, you calculate the actual oxygen demand of the process, and based on the oxygen demand, you calculate the amount of oxygen that has to be provided by the aeration system to the process. And here, basically, our work begins. You can design low budget and the opposite for low OPEX, high efficiency, and everything in between. And this is a wide span of possibilities that you have, and you can save in the design already about 40% of the energy that the aeration system then later on will consume. So we have a big leverage here in the design. How does it usually work? I'll show you a simple example of how you can design it. You see on the right-hand side two pictures of aeration systems in a test tank, very simple, based on disk diffusers. And you can see on the left-hand side what this actually means, where the difference is. I basically put it in here already. 5.1% with the first one with the low diffuser density, and 6.7% per meter with the higher diffuser density. So the design parameter diffuser density is the one significant parameter where you can influence the efficiency of the aeration system. It's basically adding diffusers. And in your entire wastewater treatment plant, you will not find another technical device where you simply add a few things and you save significant amounts of energy. This can only be done with the aeration system. That is no rocket science. That is basically a simple trick. It's based on physics. The reason why additional diffusers reduce the energy is simple. If you want to achieve a certain SOTR, or later on in the process, a certain dissolved oxygen concentration, and you use a low amount of diffusers, you have a relatively high diffuser throughput rate. We took out the figures here on purpose. We talk here about high diffuser throughput rate and low diffuser throughput rates. If you have detailed questions, of course, you can later on always get in touch with us and ask what is, for a certain layout, the actual throughput rate. This differs from plant to plant. It's dependent on the size, the water volume, water depth, etc. But the principle stays the same. The more air you put through the diffuser, the lower is the efficiency. This is the red dotted curve here. If you increase the diffuser density, the efficiency goes up. This is shown here by the 3 different densities that we have here. If you do it based on one SOTR, what happens is exactly what you see here. The operational point, red here on the right-hand corner, moves up to the left-hand corner. Of course, the diffuser throughput rate per diffuser goes down. Here in this example, we tripled the amount of diffusers. So you divide the airflow rate per diffuser by 3. Every diffuser gets only 1/3 of air, theoretically, but this is not all. Since you increase the efficiency of the system by increasing the density, the resulting airflow rate is even lower. It's not just divided by 3, it's even lower. And that basically means you have a higher efficiency, you put less air through it, you save air, and therefore you save energy. That is a simple trick, but this is how you can improve the efficiency of your aeration system easily. In this case, we are basically lifting the SOT only by adding diffusers by 30%. Another layout parameter, which is of course important, is the distribution of the aeration of the diffusers in the tank. This is also, of course, related to diffuser density, but there is another effect you have to take care of, we take care of when we do designs, and that is the vertical velocity of the water between the diffusers. If you put only a few diffusers in the tank, you get a spiral roll between all the diffusers, which basically means in the location where the diffusers are, you lift the water. And with the lifted water, you increase the velocity of the rising bubble. And this way, you reduce the retention time. So it is one principle, design principle for highly efficient aeration systems is not to move the water. Simply avoid spiral rolls, avoid massive water motion. If you see in your aeration tank that the water is moving massively, you know that you spend the most of energy on moving the water. And everyone who carried water knows how much energy that takes to move water. So a perfect aeration system does not move the water much. Of course, it provides mixing in a sufficient way, but it avoids spiral flows. If you avoid the spiral flow, you increase the retention time of the bubble in the water. And therefore, of course, the bubble has more time to release the oxygen into the water. That means per amount of air, per whatever, so and so much cubic meters of air, you release more oxygen into the water, which is basically how we define efficiency of an aeration system. To use as much oxygen as possible from the air you provide to the system. But design is, of course, one thing. Another important point, of course, is the diffuser type. What I just showed you is, again, here was the 2 red dots. It was about this diffuser. And what you can do with the disk diffuser, you can increase the efficiency by increasing the number of diffusers. And you come up from, in our example, I think it was 5.1 to 6 point something, which is good and already remarkable. But there are other options if you change the type of diffuser. And we are today focusing on what we call the strip diffuser. We call it the SSD. First S stands for smart, so we call it the smart strip diffuser. This product is designed for low diffuser throughput rates. And what makes the difference between other diffuser types it keeps its activity over the entire range of the membrane area. If you reduce the throughput rate per membrane area with a disk diffuser, you can go down to a certain level, but again, then you see that certain membranes do not open up anymore, or the consistency of the bubble pattern in your tank suffers. And with that, of course, the efficiency suffers. So the curve for each and every diffuser goes up when you reduce the throughput rate, but there are limits depending on the diffuser type and the perforation used. So at a certain point, every diffuser basically reduces its active membrane area when you reduce the throughput rate through the diffuser further down. And there, yeah, it might be a disadvantage of the disk diffuser, but it has its right in certain applications. So this diffuser is not a no-go. It is a quite common, it's basically the state of the art. But there are other opportunities, other options that you have when you use a diffuser which is actually designed for low airflow rates, designed for low throughput rates, because these kinds of diffusers, and here in our case, our strip diffuser, can then achieve incredibly high efficiencies if you design the entire system for it. Where we usually design these systems between 4 and maybe 7% per meter, tube diffuser systems somewhere in between, you can design with the strip diffuser for efficiencies up to 11% per meter. If it makes sense, of course. It's not always that we find out we can do it like this. It's really dependent on the border conditions. If it makes sense, we do it. And the sense behind it for us usually is does it economically make sense? And this is something I will talk about a little later. Basically, the simple truth behind the optimal design is increasing the SOTE. And if we take figures like we just had, 30% increase of SOTE, you can easily calculate this results in a reduced airflow rate of roughly 23%. And this translates directly in the energy consumption, which is then reduced also by roughly 23% for the system. And if you do that, and if you calculate now the total costs of ownership for an aeration system that saves 30%, then you will see that the energy costs play a major role in the entire calculation. This, of course, depends on the price of electricity. It is a difference if we do it here in Europe or if we do it in Saudi Arabia. That is a significant difference. But for each and every system you calculate, you will find out that energy plays an important role. And quite often the result is that it shows clearly that the maybe more expensive, highly efficient system pays off relatively soon due to the reduction of the operational costs. I will show, this is a topic in the agenda where I basically take a shortcut. I will show how this can, how this happens in a real case later on. Wastewater treatment plant of Lambsa located in Poland. I would like to mention before I go into this a few more points about efficient aeration systems. It's not all about reducing energy. Those efficient aeration systems are efficient because they are able to provide the oxygen in a very short time. This is also part of the efficiency. So if you run a process which requires a very fast increase of oxygen, so that the process works well. This is the case, for example, in the radar processes, as Dr. Pazou mentioned, the narrator process. There you have a phase where you need to inject the oxygen really fast. And this works, of course, the best, the more efficient the system is. You can, of course, with a more efficient system, much better react on sudden oxygen requirements, on peak flows, etc. Those highly efficient systems are really fast, and in the end, this, of course, provides to the operator a certain safety, a certain security that the process will actually work because the aeration system reacts on the needs immediately. And there's another thing which is, of course, more in the area of the CAPEX. the more efficient the aeration system is, the less air you need. And if you need less air, you can, of course, use smaller blowers. And that reduces the investment into your aeration system, and that can be significant. Now to the real-world results. I'm a little faster than planned. It's possible that we have a little more time later on for discussions, but I don't think that anyone will complain about it. Real-world results, I show only one example because it's a nice example with nice figures, clear and simple figures, and simple to understand. We equipped a wastewater treatment plant in Poland, not the largest one, but very clean and good designed wastewater treatment plant. But they specified for, we would call a low budget or low capex aeration system. And the entire specification asked for an airflow rate of 10,000 cubic meters in this plant. They needed an SOR of 580 kg CO2 per hour distributed in 8 tanks. The water level was 5 meters. We took a look at it, calculated, and said, okay, this SOTE that is needed, or the resulting SOTE, efficiency of the aeration system, is rather, I would call it mediocre, and we can do better. Calculated based on the figures, with a efficient blower, you end up at roughly, I have to say, roughly 216 kilowatt hours per hour. And this is, of course, then the figure that we take a look at if we compare it with our design. We designed the entire project, the entire aeration system, based on an average, again, based on the average SOR of 580 kg CO2, but with the goal to provide this to the system a higher efficiency. And we increased by our design the efficiency to 7.9% per meter. This reduced the airflow rate basically by almost 3,000 normal cubic meters per hour to achieve this SOR. And we managed to do it with a lower pressure loss, slightly. It's almost the same, I admit, but it's a little less with the aeration system where we put in there. This all resulted in an energy consumption of 150 kilowatt, and this is how this plant is now operated. They decided to use this aeration system. They're saving 66 kilowatt hours per hour. You can multiply that. This is a continuously operated plant, multiplied with the hours per year, and then you know how many kilowatts they are using per year. They're saving now 30.4% compared to what they originally wanted to install here. From an economical standpoint, with the energy costs that they have there, this difference results, or the energy consumption that was originally assumed was around 190,000 euros per year. You see, it's not the largest plant in the world, but it's still interesting. We got it down to 132,000 euros per year by the design of the aeration system. So they're saving roughly 60,000 euros a year. This, compared to the investment, shows very easily that the return on investment is quite short. Time for the return of the investment. The specified system was less expensive, yes. Maybe significantly less expensive. The difference was indeed 65,000 euro. In percentage, it's quite a lot. We were more than 50% expensive, more expensive than what they originally planned. Nevertheless, they did the calculation on the total cost of ownership, and of course figured out relatively easily that the additional investment was paid back in a time shorter than 14 months. And in this case, we gave a warranty of 2 years, so it was in the warranty period. And they were all happy and said, okay, that's the way they go, and that's why they decided on this aeration system. This shows clearly how things can go. Of course, every plant is different, every design is different. Sometimes we are looking at already existing aeration systems where the situation is completely different, where we see even higher or lower efficiencies and higher energy uptakes, and where we can actually increase the efficiency even more than here. Sometimes we see already good aeration systems, then of course the difference is not so significant. And in the end, everything is about the costs of the energy. If someone pays only 3 cents per kilowatt hours, then of course we don't need to talk about energy savings, at least not on a monetary side, still a good goal to save energy for the environment. And in the end, of course, it might be quite interesting to take a more efficient system to have a better reacting, better controllable device, better controllable aeration system in your facility. So there are more reasons than just what we looked at here, saving energy and money. Now to a topic which is somehow related, and that is the membrane life. We have quite often the situation that operators let their aeration systems run forever. It's 6 meters under sludge, and they don't care. Of course, you spend more energy than you have to spend if you pick the wrong device, like surface aerators. Yeah, they have a few advantages, but in the end, they consume a lot of energy and are quite often not the right choice. Let's put it that way. And then we see quite often plants where operators let the diffuser system run and run and run, even if it's obviously not working anymore, like here on the picture in the center, or if certain areas are not active, like the picture on the right-hand side, they let it go and they keep operating it. This causes massively increased costs because if you have an aeration system like that, you spend your money on simply putting air in there, but not oxygen. And that is, of course, not what you want. There are quite interesting investigations or research work on this topic in general. Dr. Stenström and Dr. Diego Rosso is the name actually. They did very, very detailed and sophisticated investigations on how aeration systems change over the time. And what is highly interesting is that they found out in all the 94 wastewater treatment plants they looked at that within the first 24 months, they saw that the most massive decrease in efficiency of the aeration systems. And in the literature, they say up to 40%, which is really a lot. This is, of course, based on layers, crusts, biofilm on the membranes that reduces the efficiency of the product. And you can do something against it. You can, of course, install a routine for maintenance or cleaning the membranes. This is, for example, flexing the membrane on and off mode, putting air through, shutting them off. Frequently, I would say, not all the time, of course, from time to time. This has indeed an effect, a positive effect on the pressure loss and the efficiency. If that does not help much, then you can, of course, do manual cleaning that is working too, or acid dosing. All those measures only work to a certain extent. You never get back to 100% to the efficiency or the pressure loss that a new diffuser has. But you do something and it helps to a certain extent. Of course, it costs time and it costs money, and all those measures contain the risk of harming or damaging the diffusers. The most effective way to get back to the full performance of your aeration system is, of course, to replace the membranes. This is quite often not easy to do, costs money, needs to be considered quite closely. But as a matter of fact, and it's a quite complicated graph on the left-hand side, which I will explain to you. If you look how the pressure increases over time, and you let it run, and this is based on those investigations of Diego Rosso and on other investigations of the Technical University of Darmstadt and of Vienna here in Europe, every system goes up in pressure loss over time, which is now here shown in a very simple way, of course, with the red line. And at the same time, the efficiency goes down. Efficiencies are here in SSOTR. This is more the European way to describe efficiency. It's kGO2, kilogram of oxygen per cubic meter provided, and meter submergence. If you divide this by 3, you get percent per meter. So if you start at a certain point, everything's okay, and then year by year, here you see the years, year by year, you see, oh, pressure increase. Now we started for 540, now we're 560, etc. If you don't do anything with the aeration system, this will go on, and at the same time, the efficiency goes down. As long as the membrane don't break, you can actually run it. As long as the blower provides enough pressure to overcome the pressure, you can operate it, but you lose your efficiency. You can do maintenance intervals like shown here in this thinner red curve, and you get the pressure down, and it's not shown here, but you of course get the efficiency up, but never to the point where you started from. So you go in a zigzag curve, higher and higher. In any case, you will hit a break-even point, but this is dependent on your facility, on the wastewater treatment plant, but you will hit a break-even point where the additional energy you use because of the lost energy and the lost efficiency and the increased pressure is more expensive than the exchange of the membrane. And in this case, you should act. If you do that, you get down, of course, get down with your pressure to the new pressure and efficiency to the efficiency of a new product. It is, I have to admit, our experience that this is not done. Because now, today, you can, of course, operate diffusers quite often longer than what we showed here, 7 years, 8 years, the diffusers in municipal wastewater treatment plant. It takes pretty long when you use, for example, the strip diffuser, you can actually operate it for 15 years and still works. But if that makes economical sense is a different question. And we recommend, if you want to run your system in an optimal way, to do this calculation, to take a look at what is the increase of pressure, if possible, by the electrical power consumption. Sometimes it's not possible to check, but actually the aeration system is taking it up. But if you have an idea about how your plant works, you can more or less figure out how much additional money you spend on the change of the aeration system. And then you should act. Now, we were asked, what are the extreme, it's a different topic now, jump now to the next topic. What are the extreme challenges for us as an aeration or diffuser manufacturer, technology provider in the MENA region? What is special about the MENA region? And compared to Europe, of course, there are two things that we have to take care of. And one is that we quite often have a problem or find the challenge, let's put it that way, that we have sand in the aeration tanks due to insufficient grid chambers or sandstorms. And this is, of course, for every aeration system a challenge. And there are certain design principles that you have to follow so that the diffusers do not get covered with sand completely. This is, of course, you can imagine easily, this would cause massive problems to the oxygen transfer to get air into the tank. There are only two simple solutions. One thing is, of course, install the diffusers at a sufficient distance from the ground. It makes no sense to really install the diffusers directly on the floor. We can do that with a strip diffuser. We can also go down very deep with a tubular diffuser. These diffusers are, by its nature, so to speak, always a little elevated from the ground. But you can, of course, elevate every diffuser. Like here, it's shown on the left-hand side with the strip diffuser that you can, of course, create the distance that you need for to be on the safe side. If the experience in the plant is that even this is not really the solution, then the next thing would, of course, to invest in liftable devices like you see here on the second picture on the left-hand side, where the entire system can be lifted out of the tank. This can indeed be a solution. It is not necessary then the strip diffuser. It really depends on what the system is asking for, what the entire process is asking for. But it can be done with disc diffusers, tubular diffusers, and strip diffusers in the same way that you can lift out the entire system. The second topic that we have quite often in project is the hot compressed air. You're facing in the MENA region ambient temperatures compared to Europe extremely high, up to, I don't even know, I would say 50 degrees or even more in certain times. And of course, the air gets compressed. With every meter of submergence, you can add basically 10 degrees Celsius. So if a tank has, let's say, 7 meters depth, almost 7 meters above the diffusers, and the ambient temperature is 50 degrees, you end up at 70 plus 50, 120 degrees behind the blower, compressed air. And if 120 degree hot air hits the aeration system, it might create a damage. So we are, of course, always taking a look at these conditions. We have the design capabilities, software to calculate the heat transfer in the pipes. And if we know that we face a critical situation in wastewater treatment plant where we think, okay, it's the water depth, it's the ambient temperature, we might have high temperatures behind the blower. We designed the entire piping system in a way that we get the air temperature down to 60 degrees at the first diffuser. 60 degrees is not the limit of the diffuser, there's a safety in there, but we try to get it down to 60 degrees simply by designing the piping system. This requires, of course, stainless steel pipes, stainless steel drop pipes. It's very important. Not so important the piping outside of the tank. The heat transfer in the pipes outside the tank is relatively low because the heat capacity of air is, of course, low. Water has a 1,000 times higher heat capacity. It takes up heat much faster. The real heat transfer, the real reduction of the temperature of the air, of the compressed air, takes place in the drop pipes. And that's why the drop pipes have an important role. You have to have the right material, and you have to have a sufficient number of drop pipes in the tank so that you get the temperature down to where it's supposed to be. And the pictures here show basically a solution for both, on the right-hand side, for both topics. These are liftable grids, all made of stainless steel, basically to be able to lift them out and to get the air temperature down in the systems. These are the main topics when we talk about proper design operation systems in the MENA region. And I think this was already the last point. There's one more slide. Right, yeah, talking about maintenance. There was a topic that I talked a few minutes ago. It can happen that you have to replace the membranes. That you say, okay, this thing hit my diffuser system, whatever it was, and now I need to do something. Or the system is simply old and membranes fail or hardened. If you have EPDM membranes in the system, they hardened. It's really difficult to get air in, or the system is not working in a good way anymore for whatever reason. Then, of course, you have to replace the membranes. And there, the strip diffuser provides one more advantage that I have not mentioned yet. One strip diffuser of 4 meters, like you see it here in the picture on the right-hand side, covers the same membrane area like 12, not making a mistake here, 16. It is, sorry, I have to say it in a different way. If you take a look at 1 meter strip diffuser, you cover 4 12-inch discs, or roughly 8 9-inch discs. And if you take a look at the time that it takes to replace those discs, you save a lot of time by simply replacing the membranes of the strip diffuser. How this can be done is shown in a video on our website. You can see it. As a matter of fact, just an example, you can reduce, if you have 12-inch discs in your system, you have to replace it, and you compare it to strip diffusers, the time for the replacement gets divided by 4. If you need 4 weeks, you get down to 1 week. For the 9-inch disc, since it's a smaller diffuser, needs additional work to replace the membranes, you can get down the time from 8 weeks to 1 week. This is significant. It's very important, of course, for the downtime of the plant, how long you cannot really sufficiently treat the water. You reduce that significantly, and of course you reduce the costs for this step significantly once you have to replace the membranes. So this is one more advantage of the strip diffuser, not only its efficiency. And yeah, the last point, do it at an optimal point in time based on an economical evaluation. It really saves a lot of money, although it sounds like a sales pitch that we are trying to sell membranes here, but it's a matter of fact that it saves a lot of money for the operator. That was it from my side already. I was pretty fast, I think. And I think now we start with questions and answers. Thank you.
Thanks a lot, Mr. Hans. Okay, so if you have any question, you can put it in the chat, and Mr. Hans or Mr. Hassan will answer it.
I think there were some specific questions regarding Ifas, so maybe I can proceed, and then meanwhile Hans Christian will have a time because he just finished the presentation, so he can then go through the questions which are related to aeration technology. I think one question was basically that there is a centralized wastewater treatment plant that treats the industrial effluent, and since some of those industries are not fulfilling the given standard, they might discharge, for example, pre-treated wastewater which fluctuates in terms of load, and can this negatively affect the plant performance, and can Ifas be, for example, used here? So I think when we talk about the load fluctuation, yes, Ifas can handle load fluctuation because you have higher concentration of MLSS, you also have biofilm technology, but then it is important to know what we are actually talking about. Is it biodegradable wastewater, or is it, for example, about toxic matters like heavy metals, which could be in the wastewater? So industrial wastewater sometimes comes from industry that, for example, they send wastewater which is hardly degradable. In this case, I think Shirkan has huge advantage because, for example, the biomass are relatively old and they are able to degrade or consume part of organic matter which is difficult to be consumed or degraded by a very young biomass. Again, to provide a better visualization, it's like you as an adult can eat pizza, you can digest it. By 6 months old baby does not have a good teeth, does not have a good digestion, he cannot do the same. So by Ifas technology, fixed bed biofilm and Shirkan, you have enough old and good biomass which are able to degrade even hardly degradable organic matter. There was a study by one of the universities nearby our facility, and they also compared various technology, and they found out also the same result even for persistent organic matter. So again, to answer, to sum up, when we talk about hardly degradable organic matter which is being discharged to your central biological treatment facility, yes, Ifas can handle even that fluctuation much better, and even you will be able to get far less COD value from your effluent. But if some of those industries are basically discharging some toxic matters, like, for example, certain heavy metals, which might result in some inhibition on those bacteria, then it is important to monitor that. Because if, for example, as I said, like bleach, for example, bleach will kill the bacteria immediately. And when we talk, for example, about the biomass, especially nitrifiers, they are very sensitive. And you have to make sure that there is acceptable concentration of toxic matter which does not result in inhibition of those biomass, so you don't face a problem. And one approach could be, for example, to put electroconductivity meter at the head of the centralized treatment facility. So electroconductivity matter is monitoring of a some parameter, means that it reflects indirectly if the concentrations of, for example, heavy metal suddenly spike or no. And this means that you are receiving a wastewater which you are not supposed to. And if you have, for example, a buffer tank, then you can basically store that specific amount of wastewater which is coming to your plant. So short answer to your question, yes, if it is about hardly degradable organic matters, it works. If there is a toxic matter in your wastewater, you have to have a good monitoring system, because any biofilm-based system or even activated sludge system will face some sort of inhibition. There was another question about sludge retention time for phosphate removal. I think our main focus at YEGE is basically nitrification, upgrading for nitrification. So all these sludges are typically calculated based on the German standard and software. But typically when you fulfill the sludge retention time for nitrification, you can also say that you fulfill the sludge age for phosphate elimination, but the BOP, the biological phosphate elimination, is very much also dependent on the condition that you create in your wastewater treatment plant, which you need to have anaerobic condition. There was another question about the dissolved oxygen concentrations that is required, or the minimum dissolved oxygen concentration that is required for nitrogen removal. So when we design the system, we typically consider about 2 milligram per liter. There are some operators that use our technology and they don't follow 2 milligram per liter because they want to further reduce the energy cost associated with aeration, and they would like to basically reduce the DO concentrations, and they set point sometimes could be about 1.7 milligram per liter, and even at 1.7 milligram per liter they do not have any problem. So for design we use 2 milligram per liter to be on the safe side and ensure that your aeration system has sufficient aeration capacity, because these concentration that you give in a design tool defines also the blower size. So if you say, for example, 1.7, then you need, for example, a slightly smaller blower, but we design by 2 milligram per liter to ensure that you have sufficient capacity, but the system also works at even 1.7 milligram per liter. There was another question about the sludge retention time for complete nitrogen removal. I think, as mentioned earlier, it is very much dependent on the wastewater temperature, and even if you have, for example, denitrification zone or no. So if you have, for example, because when you consider the sludge age here, you refer to the aerobic part of sludge age, because that aerobic part is used for nitrifier to growth. And therefore, if, for example, you have denitrification zone as well, then you might need a slightly higher sludge age. The whole sludge age calculation is also heavily affected by wastewater temperature, size of your plant, and also the reactor configuration. For example, if you have a biofilm-based system, typically you even require slightly less sludge age, because by this sloughing, from time to time, you increase concentration of, for example, nitrifiers in your system. At the same time, if, for example, I refer to the previous questions one of the audience had about these centralized treatment facilities, which is handling the industrial wastewater, then in that case, for example, it is advised to even consider higher sludge age, because from time to time, there are some part of toxic matter which, for example, have indirectly effect on the growth rate of nitrifiers. So you have less favorable conditions. So there are multiple different parameters which affect the sludge age. But if you have more detailed question, then I can basically discuss with you after the, what do you call it, webinar, because we can go through the even German standard and tell you how the whole sludge age is actually calculated. So thank you very much. I think if Hans Christian has some maybe related to aeration technology.
I think most of the questions were about the Ifas technology. There's some about the aeration system, very specific questions. I still will answer them as good as possible here without being able to show specific pictures. There's one very simple question by Mansour: is it worthwhile to install a movable diffuser system? This is, of course, very much dependent on what you need or what you want as an operator. If you want to have access to your diffusers without draining the tank, of course, a liftable system makes sense. Or if you want to be able to flush or clean your tank without diffusers in your way, of course, it makes sense to lift them out before you clean the tank. There are some good reasons to install liftable systems. Quite often we see that in industrial applications where they don't have a second tank which they could keep operating, and they simply cannot drain the tank. And then they say, okay, we need a liftable system. The major disadvantage of liftable systems is indeed the costs. Those liftable systems cost significantly more than a simple fixed system because they are usually built of steel, stainless steel, quite often high-grade stainless steel 316 Ti or whatever. And every grid that you want to lift has, of course, to be rigid. It has to take the forces that you create when you lift the system. So you're basically building like a little bridge made of stainless steel with a few diffusers on it. The cost of the liftable grids is sometimes 5 times, 6 times, 7 times higher than the cost of diffusers that you attach to the grid. And so it's, again, on the one hand, economical thing. You have to really check, do I really need it? It's nice, certainly nice to have, but do I really need it? Do I really have to spend the money? But if you have to, of course, that's the only option. If you say, I would like to have access to diffusers to get access when necessary, but I cannot drain the tank, I cannot let the water out, then of course the liftable system is fully justified and you should use a liftable system. Then there was another question about a certain technology provided by a company called Bioworks. This is a comparison between a low OPEX system where we fully cover the floor and the Bioworks system. The Bioworks system is basically a floating system where tubular diffusers are used with silicon membranes usually. For the process that Bioworks is providing, this is probably maybe even the best aeration system because they are basically creating lagoons and you cannot fix anything to the floor of those lagoons. So you have to have a floating system in a lagoon where you only have a polyethylene film on the floor. It is difficult to really install a highly efficient aeration system there. This Bioworks system makes sense. If you have a concrete tank where you can install a full floor system, fixed system or liftable system where you can achieve a high floor coverage, high diffuser density, a system like Bioworks is using would not make any sense because from an efficiency point of view, this Bioworks system is certainly not the best and not comparable to the efficiencies that you can achieve in a concrete tank where you can cover the floor with diffusers. So from a cost-effective point of view, you certainly spend more energy on a Bioworks aeration system than you would spend on a comparable system, treating the same amount of wastewater or using the same or having the same need for oxygen in a conventional process with concrete tanks. So that's all I can say about the Bioworks technology. There was one more question. I think it was already, I scroll down now. If there's any other diffuser question, what is the difference between air diffuser and operating system? Oh, that's what we just had. There was one more question. What is the difference between a disk diffuser and a strip diffuser? This is very detailed, and I probably need to show you more slides than one to explain all the differences between those two types of diffusers. Main difference I talked about is that we have a different range of airflow rate that we can put through the diffusers, and the strip diffuser has a TPU foil with a special kind of punching that allows for very low diffuser throughput rates. And as I explained, at the low throughput rates, you reach the highest efficiencies, and we reach flow rates which you cannot achieve with the disk diffuser, because this diffuser basically starts off certain percentages of the membrane area, of the punched area of the membranes, and simply does not let the air go, and this way you reduce the efficiency. So this is the design principle of the strip diffuser to make it run even at low airflow rates. It's like comparing a racing car with a regular car. It's a different design and for a different purpose. But I hope that helps. If you would like to have more information about the differences of the diffusers, please get in touch with us later on, and we can provide you with everything you need. So if there are, let me see, is there something which we missed? There's one question which starts with Ifas, but then switches the topic to diffusers. Are these diffusers efficient at 6.5 meters in biological tanks or not? As I said, it depends on the design. Of course, you can, in a 6.5 meter deep tank, you can design the aeration system for efficiency. And then, of course, you achieve with these diffusers very high efficiencies. We do that based on, of course, the requirements and the specified, what's written in the specification. And based on this, we try to find the best economical solution. This means the sum of investment and later on operational costs must be at an optimal point. This again is very much dependent on the cost of electricity, of course, but based on these parameters, we try our best, let's put it that way, to come up with the most efficient system. If this is what the tender is asking for, if it's all about low budget, of course, we cannot design for efficiency. Low budget means we need a low price. We don't want to spend much money on the aeration system. Operational costs are not important for us. Give us something cheap. Then, of course, we design it as inexpensive as possible. But this usually is not the right way to go if you want to have a properly working and energy-saving facility.
I think there were a few more questions. I'm trying to scroll down. So one was about the electroconductivity. I think we don't have really solid knowledge in that because we don't sell the monitoring system. But the salinity of the incoming wastewater, when it changes significantly, this implies that you are having a high concentration of salts or, for example, heavy metals. And another parameter, I think typically it should be about 1000 microsiemens per centimeter. But this is something that I think maybe those who are selling such monitoring system can provide better information. But another parameter that you can maybe look is the pH changes. So because when you have, for example, heavy metals, then pH concentration, for example, can change significantly. And this is also an indirect, parameter that you can basically consider that you might, for example, sending some wastewater to biology, which can harm, for example, your biomass. So pH and EC meter are useful. There was another question. I jumped. I think about the phosphate removal. How can we remove phosphorus in raw wastewater and Ifas system without anaerobic zone? That is impossible. So I think, as mentioned earlier, there are different type of microorganisms in your wastewater treatment plant that they are active under different conditions. So For biological phosphorus removal, you have to have anaerobic condition because they initially release phosphate, and then during their aerobic phase, they take more than they are supposed to, and then you get rid of them through the excess sludge extraction. So you reduce the phosphate concentration. Other approach is, of course, chemical, dosing chemical, but this is less desirable. There is another question: is it any degassing required in settlement tank? No. And another question from Mr. Samer Saber: which is more cost-effective, removing ammonia in aeration tank through nitrification, or removing in the chlorine mix tank using chlorine gas? The second part, I don't know, because I think what we are dealing is basically with biological wastewater treatment, and in biological wastewater treatment, the ammonium is converted biologically. So I think as discussed very shortly in the beginning of the webinar, there are 3 different ways that you can remove ammonium from wastewater. So one is the conventional step, which is accepted worldwide, which is the 2-step nitrification, where you have, for example, ammonium oxidizing bacteria and nitrate oxidizing bacteria. What you do here is that, as Hans Christian said, we calculate how much oxygen is required for bacteria based on the load to do the job. And then 100% of ammonium is oxidized to nitrate. So ammonium oxidizing bacteria do this job. And then there are other group of bacteria known as nitrate oxidizing bacteria, which are staying there and are ready to take that nitrate and convert it to the nitrogen gas. So this process is very solid, and it is used worldwide because you don't need to change operating parameters, and it is fairly simple and robust. Another approach, which is maybe more cost-effective, is Anomox-based solution. So Anomox-based solution is more complicated because you have to firstly make sure that the dissolved oxygen concentration does not increase, because after 0.2 milligram per liter, it does not work well. And also, it is more cost-effective because you basically, instead of oxidizing 100% of ammonium to nitrate, you only oxidize 50% of ammonium to nitrate, and then 50% nitrate plus 50% ammonium is taken by this bacteria, and then is converted to the nitrogen gas, and at the end you get only 10% as nitrate. So you need a small post denitrification. But the problem that this technology is not used widely in the mainstream means that in large wastewater treatment plants, is because these Anomox bacteria are sensitive and are having much less growth rate. So if something goes wrong in your wastewater treatment plant, you have to wait for 3 months, up to even 3 months or even more, so that you have enough concentration of this bacteria in your system. So what is used is that they use this Anomox as a side stream treatment, means that if you got anaerobic digester, then it might make sense to, for example, use Anomox for side stream wastewater treatment, because the incoming load of ammonium from your digester typically could be up to about 15 to 25% of the entire ammonium load of your wastewater treatment plant. So if you can treat this portion by Anomox bacteria, then it could be, for example, one cost-effective approach. And by side stream application, you have more control on the operating condition. So that is basically the common approach that we have. I think for the chlorine mixing tank and so on, we haven't come across with such topic yet, but these 3 methods that I mentioned to you, the 2-step nitrification, or Anomox, or Comomox. But Comomox is currently, I think, being investigated. But if you go to any wastewater treatment plant, most likely they use the conventional 2-step nitrification process, and some use basically Anomox-based solution as the most cost-effective approach, but only for side stream treatment and not for the mainstream. So I think there are no more questions related to the Ifas. So from my side, I really enjoyed, and thank you that you spent your time today with us. And if there is any specific questions, inquiry, just feel free to reach out to us, or smart sustainability, aqua energy. and we will be, of course, in touch with you and provide more detailed answer. I don't know if Hans Christian would like to answer some questions, or I would like
I
to...
think, yeah, time is up. We have a few seconds left. There's one question where I'll give a very short answer. Is it feasible to replace horizontal brush aerators in a 3-meter oxidation ditch with diffusers? Simple answer, yes. Send us your inquiry, we will take a look at it. 3 meter is not the optimal depth for fine bubble aeration, but in general, it is possible. And that was it, I think, for today. Thank you very much, everyone who was listening and everyone who was discussing with us these topics. If you need more information, please get in touch with us or with Smart Sustainability, Aqua Energy, and we will do our best to answer your questions. Thank you very much.
Thanks a lot, Mr. Hans and Mr. Hassan. We'd like to sincerely thank all of you for your attendance and engagement today. A special thank you to Mr. Hans Christian and Dr. Engineer Ihsan Mohammed Bajo for their highly valuable and technically rich contributions. We hope this webinar has provided practical and applicable insights for your facilities. Thank you once again for joining us. We look forward to welcoming you in our upcoming technical sessions. Have a wonderful evening. نشكر حضراتكم جميعا على حضوركم وتفاعلكم في ويبنار النهارده، وشكر خاص لمستر هانس كريستيان والدكتور المهندس احسان محمد باجو على العروض الفنيه القيمه والمحتوى العلمي المتميز. نتمنى ان الجلسه تكون قدمت قيمه عمليه قابله للتطبيق. شكرا لحضوركم ونتطلع لرؤيتكم في الفعاليات القادمه.